All right, folks, good morning. The original time for this lab, when this was still going to be a ground-based course, was Fridays, and I believe that the lab started at 8 a.m. And of course, it's a 4-hour lab during the summer, so 8 to 12 was the original schedule. I'm making an executive decision about this because even in the best of times, I have a really difficult time getting students to show up for an 8 a.m. lab. Maybe it'll be easier when there's not a commute to and from the classroom. I don't know. But either way, I think it's probably best. We're going to start these things at 9 a.m. and that's going to work pretty well. Um, so in subsequent weeks, that's when I'll be showing up and I'll record messages like this where uh, I'll give you whatever guidance I can give you about that week's lab. And if people are here live, they can work together amongst themselves to get stuff done. Otherwise, watch the video, do it on your own. They're all things you can do in the safety of your own home anyway. So it's not super vital that you be here, but it is possibly helpful because sometimes these labs get pretty complex. This week, however, the lab is really, really simple. There's not a lot going on because we haven't learned a lot of physics yet this semester. And what we're going to be doing is we're going to be verifying the Coulomb Force law using a simulation that we have on the FET website, because we're going to be using a lot of those during the quarantine, because it's easy to deploy and it gives you a chance to play around with some data, and that's really what I care about. So the question, of course, becomes, how do we verify a relationship? How do we actually pull off the experiment we're going to pull off today? And the thing is, we've done this sort of trick before, and hopefully over time, you guys are going to get pretty used to how this works. But the basic premise is this, right? In physics, we don't always know the answers, right? We don't always know what the equations are that relate various variables. And so a lot of times we have to do something to figure out what those relationships are. We want to be able to deduce what the equations are that relate things. And the way that invariably works is you go into a situation with two things that you think might be related to each other. And there's usually a plausible reason why you might think that might be the case. So, like, for instance, let's go back to kinematics for a second. Imagine that I'm trying to figure out the mechanics of falling objects. And it seems plausible, even if I didn't already know the answer, to speculate that there might be a relationship between the height from which I drop an object and the amount of time that it takes for that object to hit the ground. It doesn't seem too far-fetched to assume that those two things might be interrelated. Now, that suggests that I ought to be able to find an equation that relates those two things, right? If I didn't already know what that equation was, I at least could speculate, yeah, there probably should be one. If I drop it from a higher height, it probably will take a longer amount of time. There ought to be a relationship between those two things. Now, if I wanted to figure out what that relationship was, the way that I would do it is I would design an experiment in which those two items were my variables. Now, in any experiment, we always have something called the independent variable, right? The independent variable is the thing that you are choosing to change. I can pick whatever value I want for the independent variable because I have full control over it. Now, in this experiment, the thing that I probably have the most control over is the height that I drop it from. I could pick any height that I want, right? If I want to make it higher, I just lift it up higher. It's no big deal. It's not so easy to choose outright what the time is. It's hard to be able to say, okay, I want it to drop for 1 second because I can't necessarily know that it's going to take 1 second before I measure it. So what we'll do is we'll use time as my dependent variable. I'll choose my independent variable. I'll pick a height, and then once I've picked that height, I'll measure whatever time I get in response. So that's the time depends on what I've chosen for the height. So we'll do that experiment. We'll pick a height, measure what that height is, drop the object, let it fall, measure how long it took, and that's one data point. Then I'll go back and I'll choose a different height. Presumably, when I drop it from a different height, it will take a different amount of time. That'll be a second data point, and so on and so forth. I'll do this a bunch of times. And if those two variables are related to some way or to each other in some way, as we expect that they should be, then the way we'll deduce what the relationship is by taking those data points and plotting them and making a graph. And we spend tons of time in math classes learning how to look at a graph and figure out what the equation is from that graph, right? We know what those graphs of different equations ought to look like, and we can fit those curves. And that's how we would deduce what the answer is. And that's what we're going to be doing this week. We know that the Coulomb Force law relates several variables. Specifically, what variables? Well, what is the Coulomb Force law? Let me see if I can't switch cameras, and we'll run through it. Messy table, and there we go. So, we learned the other day that the Coulomb Force law looks like this. And what that means is that there's a relationship between how much force is exerted by a pair of charges and how much charge there is for the two charges and how far apart the two charges are. So you'll notice there's more than just two variables here. So in order for me to verify this law, I need to be able to verify all parts of that law, right? According to this, the amount of force that I get ought to depend on how big the charges are, but it also ought to depend on how far apart those charges are. So I can vary each of those things independently. And in order for me to do this experiment, the trick is to only ever have two variables at a time. You don't want to change multiple things, because if I change both Q and R, for instance, well, that's two things that just changed, and it won't be immediately obvious to me whether the force that I get is larger or smaller because I made Q different, or whether the force is larger or smaller because I made R different. So by only changing one thing at a time, it becomes clear that the impact on the dependent variable will be completely attributable to whatever that one thing is that I've changed. So if I want to verify this expression, if I wanted to deduce what this law was to begin with, like when we figured this out, we did experiments that were way more complicated than what we're doing in this lab, because we don't have a really good ability of choosing this outright or choosing this outright or measuring this directly. But this will be simplified. But if I wanted to deduce this, the trick is I would choose an independent variable and a dependent variable. So let's imagine that I've got a pair of point charges, right? And Q1 I can pick, Q2 I can pick, and R I can pick. I can pick any of those three things, right? What I might do is I might hold all but one of those things constant. So for instance, I'll pick a number for Q1 and I won't change it at all. But I'll pick a number for Q2. I won't change it at all. What I will change is R. Now, what's going to happen is, according to the Coulomb Force law, if R gets larger, F ought to get smaller. And in fact, if I took a bunch of different distances and I measured those and then plotted the associated value of F for each of those plots, what I would get, if this is my relationship, is a hyperbola, right? It would go off to infinity as R approaches zero, and it would asymptotically approach zero as R goes towards infinity. That's what I would expect to see. Now, the problem with that is that curves are annoying, because I can think of lots of graphs that create weird curves, and a lot of them are going to all look alike. And so usually what happens is, if we didn't already know the answer, it would be very hard to deduce the answer from something that looks like this. That's very tricky to make any conclusions based off of it. So instead, what we would do is we would plot this graph in a way that makes it linear, because the cool thing about straight lines is that straight lines are obvious. You can tell when a line is straight. So what I would have to do is to plot this function in a way that would make the line be straight. And I can do that with a clever choice of variables. Because notice, if I look at this relationship up here, in this experiment, K is a number. It's never changing. Q1 is a number that we picked and didn't change. Q2 is a number we picked and didn't change. So all of this up here is just some number whose value we've chosen. And if I rewrite this in a slightly different way, what if I write this as F equals K Q1 Q2 times, well, this would be 1 over R squared, right? This is equivalent. I just wrote it a different way. However, if I look at this and I think about how would I make this expression be a straight line? Well, if I plotted it, if I treated F as my Y variable, and I treated this entire expression here as my X variable, then what I would have is Y equals some number. Remember, this is just a number that's never changing, times X. Well, maybe I call that number M, right? I have Y equals MX plus B, where B equals 0. Oh, look, that's the equation of a straight line, right? So what's going to happen is, if I do this experiment where I keep these constant and I keep making this larger and measure the appropriate F, and I plot those graphs not like this, but instead where F is my y-axis and my x-axis isn't R, but instead is 1 over R squared, then what's going to happen is that line will be straight. And what's more, the slope of that straight line would equal K times the product of whatever the Q's were that I picked. Had I picked the higher Q's, I would have got a steeper line. If I picked smaller Q's, I would have got a shallower line, right? So how am I going to verify the Coulomb force law? Well, at least that aspect of it, the dependence on R, I would be able to determine by picking some values of Q and noting what they were, plotting F versus 1 over R squared, and if I did, I'd get a straight line whose slope ought to equal K times the 2 Q's that I picked. And I could experimentally verify that and use that to determine a percent error in my final results. So that's one thing you'll probably have to do in today's lab. Now, notice we haven't necessarily proven the entirety of the law, because all we've really tested is that the force relates to the distance between the charges the way the theory predicts. But what if I wanted to test the other elements? We also suspect that that Q is going to make a difference. So for something like that, I'd have to change the way I approach the problem. This time, what would happen is I wouldn't want R to be a variable. I would want R to be a constant. I'd want to pick a certain distance and not change it anymore. But what I would want to vary is maybe one of these Q's. Maybe I'm going to make Q2 be my variable. So I'd keep Q1 constant, I'd keep R constant, and instead I would vary the size of Q. Now, when I plot that, what I would find is that I plot F versus Q2. Well, just looking at this, gosh, if this is my Y variable and Q2 is my X variable, then what I've got is Q2 times all that stuff. But all this is going to be a constant. So what I would expect to see if I did that experiment is I'd get a straight line from that already. I'd have y equals m times x, where in this case, the slope of that graph would be k times whatever q1 was, and I picked that value, divided by whatever the r was that I picked. If I had them further apart when I did the experiment, I would have ended up with a shallower but still straight line. And so that's the thing that you'll have uh, to suss out in today's lab. So hopefully that makes sense. We've done this sort of trick before. We did it last semester with the Kepler's Law lab, where we were verifying Kepler's Law by varying the size of my orbits and the time that it took for the orbits to occur, and you did some clever bits of graphing to get straight lines. It's the same idea, right? We do this all the time in physics. So hopefully that's pretty straightforward. It shouldn't take you very long to knock this out. I also wanted to take a moment while I've got your attention, and I wanted to address lab reports. Part of the goal for making you guys write all of these lab reports is to make you better science writers. And I'm not always as good with feedback and getting feedback to you as I'd like to be. So let's take a moment to reiterate what it is that's going to make your lab reports get you better grades, and what's going to make you a better writer of scientific papers in general. So for that, let me pull the screen share back up. But this time, let's look at that lab report style guide. This is not the thing I wanted to share, stupid. Better. All right, so let's go back to your friend, the modules. And here's your lab report resources. And your friend, the lab report style guide, which you should absolutely reacquaint yourself with. And the goal of this lab report style guide is there we go. The goal of this lab report style guide is to sort of point out what my expectations are for your lab reports. And at this point, everybody who's taken this class has done this sort of stuff at least once before. You sort of know what to look at. But even after having read all this, sometimes what I find is that students don't quite have a handle on what it is that their lab reports ought to be doing. So let's talk about those sections for a second. You've got a background section in your lab report that has a few jobs. The big thing that your background section is doing is it's giving to the reader a big picture of the experiment that you've performed. What are you trying to accomplish? What were the physics principles that were involved? And how are those principles being applied to your specific experiment? Now, in science in general, we work by way of, generating a hypothesis and then testing that hypothesis to see whether or not our experimental data comports to what that hypothesis suggested we should have seen. In your background section, Max, enough. In your background section, what you should be doing is explaining to the reader of your lab report, this is what I was trying to accomplish, this is the physics involved, and this is what the physics suggests that we ought to see when we do this thing that we're about to see. Here's our hypothesis, and this is what it should look like if our hypothesis is correct. Now, a lot of times what I see students do in their background sections is they spend a lot of time talking about what they're supposed to be learning from the lab. And I need you to not do that, right? Any lab, there are certain learning objectives, certain learning goals that I have for you. I want you in this lab to get an appreciation of the Coulomb Force law. But that's not your objective in the lab. Your objective is not to learn about the Coulomb Force law. Hopefully, you're just going to do that while accomplishing your task. Your goal in today's lab is to verify the relationship experimentally. We're going to figure out what the equation is in this simulation. That's your goal. And so the first thing you've got to do in that lab report is to tell me, this is what I want to do. I want to verify whether or not the Coulomb Force law is accurately applied in this simulation. All right. Now, you'll have to explain to the reader what the Coulomb Force law is. So hopefully you'll do that. Hopefully you'll derive all the equations. There shouldn't be very many to this week. But you definitely want to give me the broad strokes of what I expect to see. So in your background section, I'm going to expect you to tell me that you're trying to verify the force law, that the force law is this F equals Q1, Q2 over R squared. And you're also going to explain to me how you're going to know that you verified it, right? Well, how would you know? Well, if I plot F versus 1 over R squared, I expect to see a straight line, and the slope ought to be K Q1, Q2. If I plot F versus Q, then I expect that I'll get a straight line, and the slope ought to be K, the other Q over R squared, right? That's a thing that you should tell me in no uncertain terms in that background section. In your procedure section, that's where we start to care about what choices we made and why we made those choices. And one of the things that a lot of students end up missing is, this right here. You're not giving somebody a recipe. You're not telling someone else how to do the experiment. You're telling someone what you specifically did and why you did it that way. You want it to be detailed enough that people will be able to understand, and if they wanted to, replicate your work. But what you're not doing is you're not writing a recipe. So do bear that in mind. I see a lot of people who mess that up in their lab reports. Something else that people often mess up is they tell me this. They spend a lot of time talking about like the math they did, but really what I care about in the procedure section is the things you physically do. Now, on a simulation, what are the things you're physically doing? You're manipulating the simulation. I'm moving the charges further apart, or I'm increasing steadily the charge on one of the charges in my experiment. So that's what you're talking about in your procedure section. Don't talk about math. The math should be in your data file, and you should have explained the equations in your background section, but don't talk about math in your procedure section. Another issue that I see students get a lot of points docked for is their data file. Bear in mind that if I go over here to the things that I'm assessing you on, right? I'm assessing you in your data file on 4 things. One is that all your raw data is there. If you measured it, it should be in that data file someplace, and it should be well labeled. But the other things that I'm looking for, the places where people lose a lot of points, are here. They put data in their file, but they don't give me the units. Or they don't do sig figs properly. Make sure that you format all of your cells so that the sig figs are preserved, because that's where significant figures matter, is in a lab setting. So yeah, those are the most common 8 points that people lose on lab reports, because they just forget to deal with their sig figs. If you don't know how to format things in Excel, I think I walk you through it in the Excel reference guide. I think it's in part 2, but don't quote me on that. Also, the things people lose points on is the results section. Uh, I have had many students who, when they get to the results section, they will simply say, see data file. And people who do that get like 0 out of 20 on their data section. I shouldn't have to even look at your spreadsheet. Right? It should exist, but I shouldn't have to look at the spreadsheet to know the answer to the question that you're trying to answer. In this case here, what's the answer going to be? Well, we've said in the background section that we expect that if we plot f versus 1 over r squared, we should get a straight line, and that the slope ought to be k q1 q2. So what are you going to do? You're going to, in your results section, you're going to show me, when we plotted f versus 1 over r squared, here's the graph. See how straight it is? Hey, here's the slope. See how that slope is really close to the number that we thought that it was going to be? It's this % off. You're going to tell me that. So make sure that you in no uncertain terms answer that question, because answering that question right there, that's 10 points out of 20 right there. And I cannot count the number of times that I've had students write a lab report and they get to the results section, and nowhere in that results section do they tell me outright what the answer to the question was. They often say sort of glowing generalities like, today we learned about the process of Coulomb forces, and we found that Coulomb forces were very important. No. Or they'll say, oh, our data does comply with our hypothesis, but they don't show me how. Be specific. Don't just assume, and certainly don't just say that your data looks like it should. Tell me what your data should have looked like, and then show me that it looks like you said it was. That's pretty important. I once had a student who wrote the energy conservation lab, and their results were, we have proved that energy conservation works, except they did all the math wrong in their data file, and their data very much did not suggest that energy conservation worked. Their data suggested the exact opposite. And they would have known that if they had thought about it at all, but they assumed that the experiment would work, and they assumed that the answer must have been correct, so they put that conclusion in there, even though their data file didn't support that conclusion at all. So don't be that person. The other thing you want to think about is precisions. This is another 4 points that gets very frequently missed by students. What do I mean by precision? Look at that units and sig figs handout, and it'll explain it. But the idea is that there is a degree to which you can trust any of your measurements. Even on a simulation, there is a limit to how precise those numbers are, and you should be aware of those. So people often miss that precision. I can count on my fingers the number of students who reliably verify the precision of their instruments, but every instrument that you use, you should verify the precision of it. Now, in this experiment, what are the instruments that you're using? Well, you're measuring 3 things. You're measuring the force, you're measuring the charge, you're measuring the distance. And so each of those 3 things is going to have a precision, and you're going to have to identify what that precision is. So I just wanted to take a moment to address that. We'll come back to this next week after I get the first batch of lab reports in, and we'll probably do an activity of sorts in which I force you to grade a lab and figure out what a good lab should have looked like, or what a bad lab would have looked like. So anyway, this week's lab, super straightforward. I don't think that you'll have any problems with it. I didn't put any pre-lab exercises on it, so it's pretty much just do the lab. If you've got questions, you guys know where to find me. So hopefully this will be a pretty painless start to the semester. Have a good one.